Hello, hello. There's Colin. All right, there's Brandon. All right. Oh, I
Morning,
still.
Professor.
Good morning. Good morning. Thank you. There's Brit, and I still owe you something. I know it's crazy times. I will get it. All right. There's Brittany. Hello. There's Xavier. Hello. Good morning. I mean, there is also pictures. And there goes. Well, okay. I guess I overstepped my. Okay, and there's Charlene, and there's Stephanie. And good morning, Alexis. And who am I for? Okay, and the chat. Wait, Caleb. Okay, and the chat. Good morning, Gaia. Good morning, Adenelsi. Good morning, Anissa. Good morning, Ariana. Good morning, Ryan. Okay, did I? And there's Brandon again. Okay, I thought I insulted. Okay, that's everybody. Okay, or I mean, and hello, Carolyn. Oh, whoa. Wait, and wasn't. Wait, there's an in and out. I'm sorry. Okay. We're gonna start in a second, but I just realized for and there's Nasrin. Hello. Good morning. Oh, and sorry. Oh, direct chat's going on. Huh. Okay, well that's honest. Okay. Oh, and good morning, Nasrin. Oh, double Nasrin. Good morning. Thank you. All right. Uh, wait. Okay, someone just sent me a direct chat. Good morning, Brittany. Good morning. Um. Sorry, I'm now distracted. Okay, someone's just being honest and mentioning that like registration is going on right now for class. Like I get it. I mean, thank you for telling me that. But so now I understand about registration. But now that makes me want to ask all of you, did registration just start last week? When did registration start for
Last week,
last week? And oh, and I'm sorry, does that mean that means for summer or for fall? That's for fall?
both, I believe.
Both. Both. Okay, both. Okay. April 2nd. Okay. I mean, I'm aware of that. I mean, obviously I had to put in all my schedule and stuff like, but I did, okay. And okay, just as do you see instructors in for
Yes.
fall and summer? You see the instructor names, yes? Okay. Yes. Okay. Okay. And I think they are accurate. I mean, just to warn you, there sometimes are changes in physics. I mean, I can't speak for the other side, but they should be accurate for physics for summer and fall. Um, okay. I don't know why that just sent me into a little panic, but okay. Um, it depends on the class. Okay, but for physics, depends on the physics class, or but I mean for physics, are they there? Since I
Yes.
know, yes. Okay. Um, um, and sorry, last check-in, just because this is we're doing something slightly new with the schedule. This in the fall, am I correct that, or is this your understanding that in the fall we have one in-person physics 204 class? Wait, one? We have one in-person 204 class that is me, and that is like at at 10:50 to 1:30. Yes. Okay. Okay, good. You've only seen in person. Oh, right. Oh, good point, Colin. Oh, yeah, right. Everything is going. What am I saying? Right. Everything. We are trying to move everything back in person. That's like not a coincidence, but yes, you're right. Okay. But physics 204, to be particular, you're seeing physics 204 in person, me. I'm not trying to be weird, but we're doing it differently now. So I want to, and you're seeing that it's me and it's 10:50 in the morning. It's like a double period, which I apologize. But it's a double.
Yeah.
Yeah.
Yes.
Yep.
uh,
Yeah.
Great. Okay. Good. Okay. And for what it's worth, well, I'm like negotiating after the close here, or like I'm average, I love to meet you guys in person. I'd be excited to see you guys in person in that class. And I know it's a little annoying that it's a double period or whatever, but I will say that up until this is the first semester we're making it to 10:50. It has been 8 in the morning to 10:40, like including right now, it is 8 in the morning to 10:40. So for whatever it's worth, it's a slow improvement. For I hope. I mean I hope it increases your ability to get there. All right, or to sign up, whatever. All right. But thank you. Okay, but I understand if your distraction, if your attention is divided, if you're trying to register right now, yeah, that's like almost as stressful as exams. I know for us too, almost not really. And like I warned you, I don't have your exams back. I am happy to say that I have them all in now. Like those of you who had special situation, they're all in. So thank you. It will take me a while, but you will get them back. So we're just going to keep proceeding. It's worse than that is so. Okay, someone just wrote that registration's worse than exams. Like I believe you. That is so. That's like depressing to hear. But all right, I fair enough. Yeah. All I can say about that, okay, God, it's so easy for me to rabbit hole. I'm going to start the board so I don't rabbit hole too much. We're going to get, and I'm going to in fact post I'll tell you what we're talking. And by the way, I also know I'm super behind on your homework. I'm aware of that. All I can say about that too, and that's not cool. I mean, that is not good. All I can say about that is when I'm behind you, when you guys are ahead of me, I am aware of it and I do take it into account both in the way that I teach and in your grades and stuff. Like, believe me, benefit of the doubt goes to the longer I take with something, the more generous I am with it. Believe me, and to put it mildly. Okay, so I'm aware that I'm behind you guys, and I think it is better for you when you're ahead of me than the other way around. Okay, but so why am I saying all that? Oh, because we're going to start going over right now we're going to start going over parts of the thing that I'm going to switch to screens. I mean, we're going to continue with Newton's laws and forces. So we're going to start going over this right now. And I mean literally this. Like I'm pretty much probably going to skip straight to this problem because I believe, I mean, I could back up and do this problem here. Number 3. I'm going to solicit your opinion in a second. But I believe I'm going to skip to 4 because I believe that you, for good and for bad, I believe that in the lab, you're already up to lab number 5. Like you've started dealing with, tell me if I'm wrong or right, but I believe you have already gotten some exposure and some thought going with regard to forces, Newton's laws, and particularly like diagrams, system schemas, and free body diagrams. I'm not saying you understand it perfectly. I'm not saying I would give you an exam on it right now. But am I right that you started lab 5 and you're being exposed to those ideas in the lab already? Is that correct?
We haven't done lab 5 yet, to
Oh,
my
oh,
knowledge.
oh, okay. Wait, then I am glad I'm asking. You have not, okay. You've done lab 4, which is the shooting, the ballistic
Yes.
projectile. Okay. And then, did you have a board meeting made? Or what?
Yes.
Oh, okay. And okay. And was the board meeting on like free body diagrams and system schemas?
Yes.
Okay, perfect. And on it, thank you. First of all, you should submit for points for that. I mean, thank you for the thank you for giving me that feedback. That's like super helpful. You start on Tuesday. Okay, I'm seeing the chat. Okay. Definitely submit for points if you just gave me that information, like any of you who just did. That is super helpful. And let me say that's a slight relief. Like sometimes you're not behind. I promise. It can be sometimes by this point, people have started Lab 5, and actually it's like really confusing to them if that's the case. It's not like that's a good thing. It just sometimes has happened. So, okay. Perfect for me to know. All right. Okay. Then you know what? I will try to very quickly do problem 3 right now. I'm going to tell you in advance where I'm going to be super quick, but you got to stop me because I always rabbit hole on the issue of MG and weight. Okay. So I'm going to try to do a quick, I'm telling you right now, when I get to the issue of MG, the arrow called MG, I'm going to try to be somewhat fast so I don't rabbit hole, but you tell me in the chat if if it's not clear, if you want to hear more about it, or like if it's already come up in the lab and in the board meeting and it's already confusing. All right. When I get to MG, um, there was just one other thing I was going to say. Well, yeah, okay. So this, and again, I'm not even looking right now because I'm behind. If you have already turned in this homework that I'm about to go in, if you made any kind of valiant attempt, what that means is remember, no matter what you did, that means you can still get all the points on it. If you didn't turn it in yet, then everything I'm going to say right now will hopefully benefit you. You totally still can. I'm just reminding because it's been a while because we had the exam. If you have not turned in this homework yet, you still totally can. And the only disadvantage, it just means you might not get all, well, you won't get all of the points, but you'll still get enough that it's worth still doing. Believe me. But okay. So either way, hopefully this is about to be helpful. Um, Oh wait, and there's stuff in the chat. I'm sorry. So this is what I'm about. But I am skipping to problem 3. Because I feel like, and you can stop me and back me up, but I sort of feel like problem 1 and 2, like this page right here, I feel like you can ask me questions, please do, but I sort of feel like more somehow or other that got, I think you're okay with this stuff from the board meeting from your lab. So I'm gonna go to here where I think the transit, but okay, there's something in the chat though. Over the break, you can definitely redo old homeworks. Yes. There's a question in the chat. Very good question. I will be trying to catch up with you over the break. So break. I will be trying to catch up with you guys. And yes, the best way you could catch up with yourselves or with me is yes, any old homeworks that you've gotten anything less than a perfect score, you can, if the portal is open, you absolutely, you can still submit new drafts. And honestly, to save us both a hassle or a headache. And also, frankly, if there's old homework that you never did, you still could, if the portal's open, you could still submit them. Again, you won't get all the points. And if it's like going all the way back to homework 1, you might, like have fewer points. I mean, more points taken off, but it would still be worth it. It still would be worth it if that's I would go backwards, always go backwards. Whatever you're missing or is imperfect, that's the most recent, that will be most helpful to you for current understanding for the final exam. So go backwards for sure if you're doing stuff. I mean that. Um, but also, if you look at some old homework, if you're just, whether you're trying to improve your grade or your understanding in the class, um, I would always recommend going backwards. And I would recommend if you see an old homework where you're like, oh my God, whatever, I only got 37 points out of like 50. I could get a lot more points on this. If you look at it, but there is no feedback, but there's a number, and that's possible. For whatever reason, first just look and see if now that you've had class, now that we've had class on it, if you look and you know what's missing or you know things you could do even without the feedback, just do them. I mean, not to get myself out of, but just so that we can both catch up more quickly. If you don't, if you look at some old thing and you're like, wait, I actually did everything here. And now he has talked about it. I know he's just being like then just send me a quick note and say, I really honestly don't know what I'm supposed to do with this. Why did I not get a perfect score? And it's possible. I will just write you back and say, oh, you're right. Here's a perfect score. Okay. So first look to see if there's anything you can do. Then if not, ask me for feedback. It's just more efficient for everybody. Okay, hopefully is what due Wednesday. Oh, this homework is not, I thought it was due today. Wait, maybe I'm wrong. Wait, maybe it is due Wednesday. If it is, I'll still help you right now. Sorry, maybe it is due Wednesday. I'm sorry, Colin. Hold on. Uh, I'm a real, I am real. I'll give you that. Wait. Sorry. I'm just quickly because Colin just asked. Maybe I'm crazy, and that'd be great if it is. Fine.
There is a homework 8 due Wednesday.
And that's this Newton's laws one. That's the one I'm looking at right now, or I'm ahead of myself. Wait.
Yes, it's Newton's law.
Oh, great. Oh, okay. Even better. Then I'm about to help you get ahead. I'm sorry. I thought it was great. Then no one's behind. So I'm going to help you right now get a jump start on it, or whatever. Thank you. Okay. So maybe even be, but I am going to assume that you, especially once I just skip to number 3, I'm going to assume you'll be able to retro do 1 and 2. I'm going to skip to 3 right now. Okay. Sorry. Yeah. We good? Okay. So I'm going to skip to 3, i.e. right here, multi-force warm-ups. It's still warm up. And I'm going to switch the screens, to do notes in a second. Let me give you the overview of what's happening here. I mean, again, in principle, you saw an overview in board meeting, but from here on in, it's all about forces, right? The whole principle is we've done all of the studying about acceleration, like really all of the intricacies that we've done up until now are different intricacies appertaining to acceleration, really. The fact that it's a vector, all the details are really about the belief that if you know the acceleration of a given point of mass at a given point in time, at a given point in space, if you know that, then the idea is then you can predict where it's going to be at some future moment or where it was at some past moment. Or you could predict the time at which it'll be at a certain, like you can predict the wheres and the whens of a point mass as long as you know its instantaneous acceleration. Like that's like really the premise of everything we've done up until now. Now we're saying, but how do we know its acceleration? Like, why does it have a certain acceleration? Where does it come from? And so now what we're saying is forces that. So in order to predict the position and time of an object, you need to know the acceleration. In order to know what kind of acceleration it has, what acceleration it has, magnitude and direction, you need to know all of the forces acting on the object. Okay, this is the premise of Newton's second law. I think it's time for me to switch the board. I'm going to switch the board right now. Newton's second law of motion, which is the most mathematical of the laws, says that if you add up all the forces on an object along each axis independently, you will know the acceleration of that object along each axis independently. Like it still presumes all this vector understanding that we have. So the premise of the second law, so the idea of the second law is that it's a predictor. If you know all the forces acting on an object, you know the acceleration of the object. Then you go back and use all the other stuff that we've already learned to apply that acceleration. So the question then becomes, how do you know all the forces acting on an object? Like, what are they? What magnitude and direction do they each act? Right. So the first law is telling you what would happen how to picture the absence of forces, like the base case, if you like. The third law is telling you really how to think about each force, like kind of how to identify what a force is in the first place. And then the procedures that you supposedly were discussing in the board meeting, and the procedures I'm going to like outline now are various kind of procedures for diagramming a given situation so that without any doubt, you can identify correctly all the forces acting on an object and therefore apply Newton's second law, which I'm trying to get on the board here. Hold on. I keep doing this. Okay. Um, so this is Newton's second law, right? The sum of all the force vectors acting on an object yields the acceleration vector of that object, of that mass. And the net force is directly proportional to the acceleration and inversely proportional to that mass. This is a vector equation. So what it really means, remember now, Galileo's principle of relativity, form number 4. Remember, every n-dimensional physics problem is really n one-dimensional physics problems occurring simultaneously yet independently. So first and foremost, this equation right here, which is like the fundamental equation of physics, like it's so simple, but it's so robust. Like everything we do sort of comes from this equation from here on in. And the first thing I want to tell you is that this equation, if you're living in a three-dimensional space, this equation really is three equations existing simultaneously yet independently, i.e., what this equation really means is you see what I'm saying? Like it really means add up all the forces in the x direction, you'll get the acceleration in the x direction, and in the y and in the z, et cetera, et cetera. It's that so our like job from here on in is to figure out what are all the forces acting in the x direction, all the forces acting in the y, et cetera. And that's where these different techniques of diagramming come into play. And that's kind of what these problems are about, or at least to some degree, that's what they're about, is like how to draw diagrams to identify all the forces. And okay, I'm going to dive in a second, but last bit of overview or warning. When I say diagrams from here on in, like system schemas and free body diagrams, the stuff that I believe you were getting exposed to in the board meeting, like these are diagramming techniques, but please understand they are like graphs or like vector diagrams. They're actual problem solving mechanisms, techniques. Like they're not just rough pictures just to give you an idea, like that, which is a very important thing in physics, rough pictures that give you an idea. But these are diagrams that are diagramming techniques designed so that if you follow the rules of them strictly, they will like force you to set things up correctly, and they will like perform computations for you in the same way that vectors do. If you draw them to scale and you put them tip to tail, then like they literally produce answers for you, right? That's what, so I want to show you two forms of diagramming that when, if you follow them strictly, you don't have to think, you don't have to be creative, you follow the rules and they do the thinking for you. Okay, that's the idea. So, um, so that's why we spend a lot of time on them. So yeah, I'm just gonna like go over this now as though whatever, and hopefully it'll help you. Um, am I gonna do the 5-step method all now? No, I'm gonna just try to present material. So it's still your job to put this in a form when you hand in the homework. Um, but I'll also say, like, when a question, this happens in Physics 204 sometimes. I mean, if a question is explicitly asking you as the question to provide a certain type of diagram, then you provide that certain diagram and you don't have to do other diagrams also. Well, yeah, I mean, here it like breaks down. It says draw a picture of the situation. That when it says draw a picture of the situation, sorry, I'm looking at the sheet now. When the problem says draw a picture of the situation, that is the thing that you normally do for step one. Picture and fact pattern. So in some ways, whatever you understand what I'm saying, I think, or if you don't, tell me. But um, so this is so I'm just doing this. Um, All right. So, all right. So here's my picture. We've got an apple on a table. The apple has a mass of 0.05 kilograms. It's moving at a constant velocity of nothing, which means in our frame of reference in the lab, we don't observe it to be moving at all. Okay. So that's the picture, right? Then it says, to draw a system schema now of the situation. Really, well, a system schema of the situation, which really tacitly means draw a system schema that focuses on the apple. Now, okay, again, I think you did this in board meeting. So, what is a system schema? A system schema identifies all forces relevant to the mass that's in question. Like in this case, the mass in question is the apple. I mean, of course, there's other masses, like the table has mass, but no one told us the mass of the table. The table is not the focus of the situation. The mass, ultimately, the mass whose acceleration we would ultimately want to figure out is what I mean by the focus of the situation. And a system schema asks us to identify all the forces relevant to the mass in question. Let me be a little bit more specific. And the system schema is always the first picture, or the first diagram that we should draw if we're ultimately trying to figure out anything about acceleration, if we're ultimately analyzing anything about forces acting on a mass, system schema is the first thing we draw. As said before, the purpose of it is literally when I say identify, I mean, what are they? Just make sure that we know every force that could possibly play a role and that we don't leave any out and we don't put any into our head that don't belong there. That's the main job of the system schema. Each force Okay, what's important is here's where Newton's third law comes into play. When we're trying to figure out what forces are acting on an object, which is the point of the system schema, what we do is we remember Newton's third law. Newton's third law is really the law that's really telling us what a force is in the first place. And what a force is in the first place, well, in roughest terms, a force in the first place is a push or a pull. Like literally, every single force in the world is either a push or a pull. It's not anything else, and it's not both at the same time. Every force is either a push or a pull. Now that's like English. That's not really like a rigorous, like scientific way of putting it, although it's true. I mean, it's right. And it'll never fail you, I might add. But what do I mean by a push or a pull? I mean a symmetric interaction between two material objects, like two real, concrete, identifiable, physical, tangible, countable things in the world. And the proper name for that in physics or science is a particle, right? I'm saying for there to be a force of any kind anywhere, one thing must be pushing or pulling one other thing. I'm like really serious about this. And it's like it gets lost on people a lot. A force is not something you have. A force is something you do to something else. Like for real. So we say so a baseball bat does not have a force. A baseball bat exerts a force on a baseball. And when it pushes a baseball. And when a baseball bat exerts a force on a baseball, the baseball exerts a force on the baseball bat. Like they're just pushing against each other. Like that's what we mean by a force. And we sort of are encouraged to picture that from the way Newton's third law is written. So every force we're ever going to identify is a symmetric interaction between two material objects or two particles. And that's what the system schema is going to ask us to do. So specifically, to do a system schema, we first, we first draw a dotted circle, like in the center of our, like the space on our paper. We draw a dotted circle that always dotted, that represents the mass of focus, the center of our attention. So it's labeled M. And again, remember, this is all about F net equals MA. So always the M in F net equals MA is the thing that we're paying attention to. We're always ultimately trying to figure out what are all the F's acting on the M so that we can figure out the A of that M. And again, let me just say again, too, even though that's what the second law is saying, is that if you add up all of the forces acting on an object, you will thereby know the acceleration of that object. That's the correct way to interpret F net equals MA. There's many wrong ways to interpret it. That's why I have to keep sort of saying that. I don't want to say the wrong things, but the M in that statement is the receiver of the forces and therefore the object that gets accelerated. Force is being viewed as like the cause, and acceleration is being viewed as like the effect, for whatever it's worth. So we draw a dotted circle representing the M, and then we're going to draw a solid circle for any and every, and you may want to be writing these instructions down in English on your notes. I'm sort of trying not to rabbit hole, so I'm not writing them, I'm saying them. But first instruction is you draw a dotted circle representing the mass of focus. Then you draw a solid circle for each and every object in the world, in the universe, that you believe is meaningfully interacting with our mass of focus. I mean, in this case, the apple, right? You're going to draw a solid circle for every object that is pushing or pulling on the apple. Now, how do you know what objects are interacting with the apple? I'm trying to decide whether I want to say this first or write this down. I'll say it. The way to know if something is, and this is a 100% unambiguous way once you hear it, the way to know whether something is pushing or pulling on something else in physics is to say that for something to be able to push or pull something else, it either has to be pushing or pulling gravitationally, i.e., it has to be planet Earth, or it has to be touching the object. It's that simple. Like at least in this realm of physics, of classical mechanics, of Newtonian physics. In other words, what I'm saying, we will write this as a rule in a few minutes, but I'm saying the only way to push or pull something, the only way to exert a force on another object in classical mechanics is to touch it unless you are planet Earth pulling on it through this seemingly mysterious, but apparently always there phenomenon called gravity. I'm going to say it one more time just because gravity at this stage is the grand exception to like all of our physical rules. When I say this stage, I mean this stage in the class, and I mean this stage in history, in the history development of physics. I'm not trying to be weird, but I'm trying to say that physics is actually remarkably simple, or the study of forces is remarkably simple, as long as you always recognize that gravity is a phenomenon that's there even at this stage, even at the year 1697 or whatever, for centuries, we all know that when you let something go, it falls to the surface of the earth. And we even by this point know that it's going to fall at a constant rate of acceleration, approximately 9.8 meters per second squared or whatever. Empirically, it's just impossible to deny that perpetual observation that the center of the earth seems to pull on anything and everything near it toward it without touching. It's so there that we're all familiar with it. It's so true that we all have to incorporate it into our understanding of the physical world. There's this phenomenon called gravity, but it's also really exciting, and we're so used to it that we can sometimes take it for granted. But we have to recognize that the thing that is intriguing and mysterious about gravity, even at this stage of history, and for a long time, I mean, even into the early 20th century, what is intriguing and mysterious about gravity is that it acts like a force. It is a force. It pulls on objects. It pulls in a totally predictable scientific way, but it seems to be able to pull without touching. Like the earth seems to be able to pull on rocks or pencils or whatever, you let go in the lab. The center of the earth seems to pull on things without touching things. That is an exception that inspires curiosity if you want to be curious about it. All other forces that we know to this moment work by touching. So the rule in general is in every single, the absolute rule is in every single system schema. The first thing I'm going to do is draw a solid circle somewhere. I don't care where. I'm not even going to draw it under the mass, just anywhere I want. I'm going to draw a solid circle, and I'm going to label that circle either EE for entire Earth, like some websites and books will do that, or CE for center of the Earth, because it seems like it's the center of the Earth that pulls everything toward it. However, or PE for planet Earth, if you like. But I'm going to draw some circle somewhere in every single system schema because it's always there and it's always pulling on every single object that I ever look for. And so then I'm going to draw a solid line connecting the planet Earth, the center of the Earth, to the mass. And that line represents the fact that no matter what, the Earth is pulling on the mass, and therefore it's a force, so it's a symmetric interaction. So therefore the mass is pulling on the Earth. Like it's just a line. There's no priority. Now you might even ask me, I'm going to go on in a second. You might even ask me, why did you draw the Earth like flying up there to the left? Like, why didn't you put the Earth under the mass? Idiot. The reason I didn't is because I'm trying to emphasize that in this diagram, we are not at all concerned about directions. There's no arrowheads. There's no directions. This diagram is there. The purpose of this diagram is entirely to identify what is pulling on the mass, because honestly, that's hard enough and important enough that we're doing that first before we even get into the issue of direction. So I'm deliberately putting the Earth in an arbitrary place to super emphasize that I don't care at all about whether it's pulling up or down or anything. Okay. So let me summarize okay. So I've drawn the Earth. Now, okay, I'm going to write this down, but I'm just trying to get it out there first. I'm trying to say in every system schema, no matter what, you draw a dotted circle that signifies the mass in question. And then you always, the next thing you do is always draw a solid circle that represents the Earth and a solid line connecting the two, because the solid Earth will always be there in every mechanical situation, always pulling on your object no matter what. So it's always and so first of all, it's always there and it's always playing a role. That's important. But second of all, it's easy to forget if you don't write it first, because it's the one object that will be pulling on the mass without touching it at all. After you've drawn the Earth, then you draw a solid circle for any and every single object that is in any way touching the mass, in this case, touching the apple, like in the basic sense of the word touching, like material contact, like no tricks up my sleeve, right? So in this case, it would be the table that's underneath the apple. It's like in contact with the apple. The table is touching. Yeah. So I'm going to draw a solid object for the table. I'm going to label it table, or whatever it is. I mean, in this case, it's a table. And I'm going to draw a line connecting it. Again, they're just like flying out there because I don't all at this diagram. Sorry. And then that's it. There's nothing else touching the apple. Like, I mean, are air molecules touching the apple? Yeah, actually, I believe air molecules probably are. And if it were a sophisticated enough physics situation where they're literally starting to give you facts about like the fluid drag or like the air resistance, exerted by the air, if they started talking about the air in any way that started making it relevant to the problem, then maybe I'd put that in. But number one, they didn't do that here. There's no one's making any reference to the air. Second of all, also, honestly, air is a gas, not a solid. And this is classical mechanics. So what we're really talking about here is solid objects. Okay, so any solid that is touching the mass gets its own solid circle in a line connecting to the mass, and that's it. So what I'm saying so far, as far as how you draw, and this is it. There's nothing else touching the apple. So this would be my whole system schema done. I'm done, and I'd move on. But let me just summarize like what we just did here. I didn't mean to do that in that color. Sorry. Oh well. Oh, sorry. That's not. I meant dotted circle. Sorry. Okay, so far what I'm saying, of course, as usual, you can't even read what I just wrote, but I'm saying the rules that we're following so far is you draw a dotted circle representing M, then you draw a solid circle for planet Earth, center of Earth, entire Earth, whatever you want to say, and then you draw a solid circle for every single object that's touching the mass. Okay, and so what I'm trying to emphasize here is you put in Earth first because Earth pulls without touching, and then it's all about touches from then on. Like that is the standard. How do you know if a force is acting? If something is touching, and if it's not touching, it's not a force unless it's Earth. And if it is touching, then it is exerting a force. It's literally that simple. It often doesn't seem like it should be, but it is. Like that literally it's 100% guarantee in classical mechanics. Then you connect these things up by lines. as I did here, but now I want to be a little bit more detailed about that. And then we're going to go on to the next, I don't know why that thing is freaking out. Hold on. Sorry. Okay. So you connect the object by straight lines, but now in order to connect the object by straight lines, um, I want to be more specific about that. Okay. How to draw the lines. Now, why the lines matter because each line that you put into this diagram is a force, right? And just note the sort of philosophy of this diagram is that you identify forces by identifying objects that are touching your mass and planet Earth. Like you, there can't be an interaction unless there are two objects interacting. And that means real material objects. Um, so you identify the objects with these big circles, and then you connect the objects to each other with lines. Each line is going to be a force that then we're going to lift out of this diagram and put into other diagrams and into the math. Okay. So because the lines are the forces, let's be clear on how many lines you draw in your diagram. Well, you follow the one touch, one line rule with exactly two exceptions. Like this is going to sound complicated, but again, this is so that there's literally 0% error in this procedure. For every touch that you observe going on in a situation, you draw one line. But there are two exceptions to this. The first exception is planet Earth. We already mentioned Earth is no touch, but it gets a line anyway. Because for some reason, it seems like Earth does this thing called gravity. Now, well, yeah, it seems like, and it has seemed like for thousands of years, and for 4 other labs that you've already done, it just seems like the center of the Earth is always pulling down on everything at the surface of the Earth. Now, I'm not trying to be sarcastic about that. I'm not trying to like be stupid about it. Like, I believe that you believe that. What I'm trying to say is like, when we use the word gravity to this point, at this point in history and in physics, when we use the word gravity, we're just using a word that to mean that phenomenon that we've all noticed. We still are not claiming that we know why or even really how gravity does what it does. We're just saying that apparently it seems to be true. Okay. So because Earth can apparently pull things without touching them, then when you put the Earth into your diagram, you immediately know it's going to pull on your mass. So it gets aligned, even though there's no touch there. Everything else, there'd have to be a touch for there to be a line, right? But there's one other exception to this one touch, one line rule. The other exception is if two rough surfaces press against each other. I'm serious. I don't know why I always say that. I mean, obviously I'm serious, but if and when you have, and by if you have two rough surfaces pressing against each other. So first of all, I mean a push, not a pull. Anytime you have a pull of any kind other than gravity, it's going to get one line, no exceptions. But if you have things pushing against each other, and the things that are pushing are surfaces, and if those surfaces have a certain roughness, and the roughness would have to be specified, like if the problem literally says that the surfaces are rough, and if it even says something mathematical or quantitative, like the roughness of the surfaces could be described by a coefficient of friction, mu equals 0.4, or so, I'm not being right, something like that. If literally the problem starts describing the roughness of the surfaces in numerical terms or algebraic terms, and you believe that those surfaces are pressing against each other, then that touch but they're definitely touching, right? But if they're touching in that specific way of being rough surfaces that are pressing against each other, then they'll get two lines. That who saw that one coming? What I mean is, so let me back. Well, I'll explain what I mean. So I'm saying from here on in the system schema, one touch means one line, and vice versa. If you see one line, that means there's one touch. Two exceptions are gravity is a line without a touch, okay? And rough surfaces pressing against each other get two lines because if you have like a hockey puck, let's say, on a table, like a hockey puck or a hockey puck on a rug, right? Then the two surfaces are pressing on each other like this. So they certainly should get a line indicating they're touching, they're pressing, there's some kind of force there. But if they're rough, that means they're going to microscopically, like they're made of like bumps and ridges on the outside of their surfaces. So they're going to like lock into each other. It's going to be like teeth of a comb microscopically going like this, which means then they're going to exert some kind of resistance in a perpendicular axis. It means like if you put a hockey puck on a rug, the harder you push the hockey puck into the rug, or the heavier the hockey puck is, the harder the hockey puck, the harder time it has sliding along the rug. You know the word for that is friction. So we're saying when two surfaces press against each other, they actually motivate or inspire, they generate a force in another direction that we call friction. When they push perpendicularly, and we call that normal, because in math, the word for perpendicular is normal. Like literally, normal means perpendicular in math. So when two surfaces push together, if they're rough and they're surfaces, if they push against each other perpendicularly to the plane of contact, then they create a force parallel to the plane of contact. So normal forces are always accompanied by frictional forces if you have two surfaces that are rough. So whenever you have two surfaces pressing against each other, we draw two lines in the system schema indicating we got to know right away that's going to be two forces in the math that we have to deal with, okay? That would even be true in this problem here. That would even be true because an apple sitting on a table is like this bottom of the apple is a surface, the top of the table is a surface. When I say surface, I mean like area, like geometric, like plane, two-dimensional region of space. That would even apply here, except first of all, the apple isn't even going anywhere, we're told. But second of all, no one ever told us how rough these surfaces are. We're assuming it's a very polished apple and it's on like a glass table or something. So apparently none of that is relevant in this problem. Basically, we don't have surfaces of any kind of specified roughness in this problem. So we don't have to draw the two lines in this problem. But the minute we get into any situation where a surface that is on a surface is pressed, you get my point. If a surface is pressing on another surface and they have any kind of specified roughness, then in the diagram, you would draw two lines for their interaction because they're going like this and they're going like that. Okay? So those are the two exceptions. Now, I'm going to be very clear about that. Like, I'm being complicated. I'm being complicated because, in a weird way, this unit of physics, this topic of physics, in some ways, is more algorithmic and procedural than even what you did, before the midterm. Like there, I was sort of trying to teach you like how to think like a physicist in a way, and of course, I'm still interested in that. But by the time we get to all these, in a way, the thinking has been done for us as long as we follow the thinking. And the thinking is so precise on how to draw these diagrams that if you literally follow the rule and know that it has exactly two exceptions. So I'm saying these two exceptions are the exact two exceptions. They don't represent that there's like a vague list of many possible like vaguenesses. You get my point. From now on, in a system schema, you draw objects and then you connect them with lines and you do one line for every interaction. How do you know if there's an interaction? Either there's a touch or it's gravity. And if it's a certain kind of touch, like this kind of touch, it's really two touches. That's what I'm saying. That's a system schema. I know that took a lot. So that's a system schema of the apple. I'm going to go back. Is there any? There's nothing in the chat. You can stop me. Well, you probably want me to just move on, I'm guessing. So I'm going to move on. So now we go to now the next. Yeah, obviously these diagrams get more complicated as the situation gets more complicated, but I am telling you that if you just follow the rules, it doesn't matter how complicated they are, you'll still like be able to manage them. And they're more worth it the more complicated they are. So the next thing in this problem is to draw an FBD, i.e. a free body diagram. Well, okay. My being completely inconsistent in the way that I'm using colors here. I apologize. But so now it says draw. Now I'm going to add the word. Okay. So it says in the problem, it says draw free, but it says draw an FBD of the apple. So first of all, again, the app, what's the apple? The apple is the mass in question. So I'm just saying of the M, okay? But also I'm adding a word here that's not in the original sheet. If someone just says FBD, they mean free body diagram, and they mean, if they don't specify otherwise, they mean a pure free body diagram. You're going to see shortly that once we have pure free body diagrams, we often then break them further down into yet a third type of super important diagram called a component free body diagram. Okay, now it turns out that's like not necessary in this problem, but I want you to know I'm really arguing here that there's like three levels of picture making in order to properly analyze F net equals MA, to properly deploy Newton's second law. There's really three levels of diagramming that we do all the time. And and I mean all the time. I mean, like if you're really doing physics, not just not even just learning physics, whatever. Um, so a free body diagram, if someone doesn't specify otherwise, they mean a pure free body diagram. Now, what is a pure free body diagram? It means it's something that you build from. I'll summarize. The summary of a free body diagram is this. Okay. The whole point now is we're going to shift. We're going to change our dotted circle into a point, And every single line that was in our system schema is now going to become an arrow, a vector in our free body diagram. And so the whole idea is that we did the system schema to make sure that we were accounting for every possible force and not introducing anything falsely that shouldn't be introduced as a force, which believe me, people do all the time. And now that we've done that, now that we feel confident, we know what the forces are. Now we start turning them into vectors so that we can do math. We start being focused on what their direction is and their comparative magnitude. So what we do now is we take what was a dotted circle, the M before, and we draw it just as a point. Okay, so M is now a point, signifying the center of mass of the apple, like signifying like a Euclidean dot, like at the center of the apple. And now each one of those lines is going to become an arrow that points whose tail starts at the dot and whose tip is oriented toward the particular direction that the force is acting in. So I'm going to follow the same rhythm as before. Whatever I started with planet Earth before, so I'm going to start with Earth again now. Earth, like Earth, made a force that we call gravity, and it pulled the object, it pulled the mass, the apple down. So I'm going to draw an arrow going down from the mass. Okay. Now, I'm not going to write Earth anymore. I originally wrote Earth. It was very important. I needed, because I don't want to ever believe that there's a force that doesn't consist of two identifiable objects interacting with each other. Like, so Earth was interacting with the fruit, the apple. So it sounds like the Garden of Eden, but Earth was interacting with the apple. So because I could literally say that's an object, I could believe there was a pull between them. So I convinced myself of that. So now I'm interested in the pull. I'm not interested in Earth anymore. I was only interested in it as justification for believing in the pull acting on the apple. It's all about the apple from here on in. So I draw a downward arrow from the apple, saying the apple's being pulled down. Okay, now I'm going to give a name to that force. Like it came from the earth, but I have a name for that force, right? Some people call it gravity. I mean, we all call it gravity, but another name that you might have picked up from the board meeting, is W for weight. Okay, the weight of any mass or the weight of any M of any object is the gravitational force due to the center of the earth pulling on that object. Like before I go any further, let's be clear. Weight is a force measured in force units, which I don't even know if I said what those units were last time. Let me get like a sidebar or a retrospective on units of forces. Yeah. I'm not even sure if I said this last time, and you've probably heard it in high school or whatever, but just to be clear before I go any further, like a force unit in metrics in SI The unit of force is 1 kilogram of mass times 1 meter per second squared of acceleration. That unit is called a Newton. Surprise, surprise. So from now on, any force that is measured in newtons. So weight is a force. Weight is the word for the gravitational force acting on an object. The part that I want to, the part that that homework tries to explain to you in part 2 above, the part that it asks you to think about in part 2 above, and the part that you may have already thought about in the board meeting, is that, I'll just say this quick, is that weight of any object, like the weight of any object is how much gravity from Earth pulls on that object, M, right? So if you think about, if you consider for a moment free fall, we're not in free fall in this situation, but consider free fall. If an object is in free fall, that means by definition, the only force acting on it is its own weight, right? If an object is in free fall, nothing is touching it at all. Nothing is influencing it other than the center of the Earth. So in free fall, the only force acting on you is weight. Therefore, that is the sum of all forces acting on you, right? In free fall. So weight equals ma in free fall. But in free fall, we know that A is always G. It's always that like 9.8 number, right? So the weight that pulls down an object in free fall is mg, its mass measured in kilograms times the 9.8 meters per second squared number, right? Like that's your weight if you're in free fall. Well, then that's your weight all the time. Like if you're not in free fall, that means other things are also acting on you. Like there might be a table stopping you from falling. Stopping what? Stopping your weight from pulling you down. What's your weight? That. In other words, the weight of an object is always its mass times 9.8 meters per second squared. The weight of an object, 1 Newton of weight is essentially 9.8 newtons of weight applies to 1 kilogram of mass. See, I always overtalk this or undertalk it. You stop me if you don't. Wait, there is something in the chat. Thank God, because I'm never. How do you know? Wait. Great question. Wait, so all right, I'm gonna finish this statement and then I'm gonna answer that question. And then I know we have 7 minutes left. The statement I'm making right now, but definitely I want anybody, again, there's something about this that I don't know why, but I always either undertalk it or overtalk it. So you just got to tell me in the chat if this makes sense. I'm saying from now on, in every single free body, just like in every single system schema, there's a circle that represents the planet Earth because it's like always there and it's always interacting with us. Now I'm saying, to be more specific, in every single free body diagram, there's a force from the Earth called weight, right? And the force acting on any mass, the force of gravity from planet Earth acting on any mass is always M times G, not M, M times G. I'm saying always the weight of an object is mg from now on. That is not how fast it falls. That's how hard it's pulled, if that makes sense, right? So that's what I'm saying from now on. Sidebar off, and I'm going to get the chat question. I am also trying to. Well, that's what the weight of an object is. Like, if you really are following what I'm saying, I'm just going to, I know you've heard before that weight and mass are not the same thing. I'm trying to say ultimately that mass is resistant to forces. One such example of a force that in fact is always in our lives is the force known as weight. Weight is not measured in kilograms. Weight is measured in newtons. A newton is a kilogram times a meter per second squared. your weight is your number of kilograms times 9.8 meters per second squared, because that's the rate at which you would fall if nothing else were pulling you or pushing you besides your weight. Okay, that's what I'm saying, but that's, you can memorize that now. Like weight is always mg. Now, there's something in the chat. How do I know? So it asks, it's a great question, and please apply for points for this question. Not apply for points, whatever, submit for points. How do you know which direction to draw the arrows for the free body diagram from the system schema? Great question. Yes, because you're right. We're going to take any line from the system schema that definitely was not an arrow, and we're going to turn it into an arrow. So the answer, so how do you, and yes, the answer to this matters. How are we going to turn it into arrows? You draw the arrow. The arrow must point in the direction that the mass is getting pulled or pushed. And indeed, when you picture the situation, you will know the answer to that question by picturing the situation. But yes, you have to think about it, and sometimes it's less obvious than other times. In the case of so I'll give you another example in a minute. Like I'm going to do the other arrow, so you'll see. I mean, it's maybe in a way as hard as it gets. Like the gravity arrow, mg, the weight arrow, that's always down because Earth is always under us, pulling us toward its center. How do I know that Earth is pulling us down, by the way? One way I can test, and it's the same way I would test any other arrow to answer your question. If I were in free fall, like to say, the reason I'm like thinking about free fall, even though this is not free fall, is it's a way of saying all other things being equal. Like if I get rid of all the other distractions and just focus on what the Earth is doing, if there were nothing else there, then I would accelerate down, right? That's how I know the Earth is pulling an apple down, is if the table weren't there, the apple would accelerate down, it would fall, right? So that's how I know that the Earth is pulling down. So I make the arrow down. Similarly, just to answer your question, and actually I should have given myself more room here. Sorry, hold on. Similarly, I'm not changing this, I'm just making it smaller. Similarly, there's this other line in the system schema. The other line in the system schema represents the table pushing on the apple. Now, in some ways, this, what I'm about to say about the table, and I know we'll be done in 2 minutes, perfect to end on this question. Thank you. The table is pushing, I mean, the table's underneath the apple. It's pushing the apple up. Like the answer is the table is going like this. Okay, how do I know that? And don't worry about the size of it for the moment. I'm just saying direction. The table is pushing the apple up. How do I know and that may even seem weird to you. You might think, no, it's just like holding it. Well, holding it what? Holding it up. It's pushing it up in the sense that, number one, if the table weren't there, the apple would fall down. So the fact that the apple is not falling down means the table is doing something opposed to gravity. It's pushing it up. Okay. Furthermore, if the table were, I mean, this is like a weird thing to say, but if the table's not made of magnets, the table's underneath the apple, but it's not made of magnets, so it's underneath the apple. It's not pulling the apple toward it. If it's in contact with the apple, but it's not made of magnets, if it has to be a choice, I know to some people it seems weird to call this a push because like the apple's not moving, but we want to get used to, we're not saying forces and accelerations are the same thing. We're saying they're related. The table is pushing the apple up because if the table weren't there, the apple would fall down. So the table's pushing it up, and push means away, pull means toward, and the table is underneath the apple. So it's up. That's how I would, anything else, even if it gets more complicated, like, that's how I'm going to do it. I'm just going to ask myself, if that force weren't there, what would be happening? Or if other forces weren't there, what would be happening? The last thing, we have 1 minute. The last thing I want to say is, here in this arrow again, I'm not going to write table anymore. Table was what I first wrote in the other diagram. So I had proof in my mind that there was actually an object in the world that was actually exerting this force. Okay, but what is the force? I want to know now. There's a name for this force, just like there's a name for the gravitational force. We call it weight and mathematics. Like I want to start putting these in ways that I can do math with, right? So the name for this other force is capital M is the normal force. And that just means normal is the word we use when when two surfaces are pushing against each other, when they're pushing perpendicular, normal means perpendicular. When two surfaces are pushing against each other, if you imagine the two surfaces are like two pieces of bread, then there's a piece of bologna. It's like a bologna sandwich. There's a piece of bologna between the two pieces of bread. It's 12:05. Sorry. Sorry. I forgot. Okay. So anyway, if two surfaces are pushing perpendicular to the plane against which they're sandwiched, right? If they're pushing perpendicular to the plane, we call that normal. So it doesn't matter if it's a table or if it's an apple or if it's a rug or if it's an ice skating rink. And it doesn't matter if they're rough or not. If they're pushing perpendicularly, we call that perpendicular contact pressing force, the normal force. That's okay. Yeah, sorry, you have to go. That's the free body diagram. That's to answer your question. We'll pick. Oh, great. Yes, have a good day. Yes, thank you. Okay, see you in 2 days. Okay, you're very patient. Oh, what am I doing? Okay, well, I'm turning off the room. If you have a quick question, you can ask when I'm turning off the